Hey everybody, I've got a very short lecture for you guys today. It's lecture 7 and it's about trees. So if you're following along in the book, and I hope you are, you'll have noticed that we've skipped the section on stable marriage. This is quite a fun section, so don't be too disappointed, we are coming back to it. The reason I've skipped ahead to trees is that this section is actually quite useful for your assignment, so skipping ahead to it gives you a bit more time to work on the assignment than you would otherwise have. As usual, even though I'm giving this lecture, you should follow along in the book. You should read the sections. Anything I don't cover in the lecture but that is in the book is still something I could test you on. And more importantly is useful stuff that you should know because it's cool. Okay, so we're talking about trees today, and the first question is, what is a tree? So from a graphs perspective, you guys have seen trees before I think in Richard's course and potentially in a number of other courses. I know they come in handy in things like networking as well. But you probably have a quite intuitive understanding of what a tree is, like a sort of, I'll know it when I see it. When you get down to an actual definition of it, what a tree is a connected acyclic graph. Okay, so it's a tree that is it's a graph that is connected, meaning I can get from any vertex to any other vertex. And it's acyclic, meaning there aren't any cycles in it. There's no way to just walk around and round and round kind of thing. So let's look at some examples. If we look at graph A, okay, is it connected? Well, yes, I can get from every vertex to every other vertex. Pick any pair of vertices, say 3 and 2. I can get from vertex 3 to vertex 2 by going like 3, 1, 2. Or even 3, 0, 1, 2. I can get there, basically. I can find some path. Is it acyclic, though? No, because there are subcycles here. I can see there's a cycle 0, 3, 4, 0, 3, 4. Like, I could walk around in circles there forever, so there is a cycle. There's a bunch of cycles, actually. 0, 1, 4, 3 is a cycle. 0, 1, 5, 4, 3, 0 is a cycle. There's just cycles everywhere, right? So A is not a tree because it's not connected and acyclic. Is B a tree? Well, if I look at B, I can't see any cycles, so it's certainly acyclic. There's no way to construct those sort of circular paths, right? But is it connected? Can I get from any vertex to any other vertex? Let's take, for example, vertex 2 and vertex 5. Is there a way for me to construct a path from vertex 2 to vertex 5? No, there isn't really. So B is not connected, okay? When I look at C, is that a tree? Well, is it connected? Yes, I can get from any vertex to any other vertex. I can get from 2 to 5, for instance, by going 2, 3, 1, 5. I can get from any vertex to any other vertex. Is it acyclic? So is there a way to construct one of those circular paths? And looking at it, it is acyclic. There are no circular paths, right? So this is a tree. Now note that it doesn't really look like a tree, right? If I drew this for you as an example of a tree, you'd be like, what? But doesn't matter. Doesn't matter what it looks like. As long as it's connected and acyclic, it's a tree. Okay? And note that it's not a binary tree. Like vertex 3 has a whole bunch of connections to it, right? So trees are not necessarily binary trees. I've noticed this misunderstanding in previous years' classes just because in first year, the types of trees you mostly dealt with were binary trees. This is not, trees are general. It can be binary or it can be not. It doesn't matter. Okay, so looking at that graph C, I'm renaming it A over here. It doesn't look like a tree. But what if I wanted to redraw it so that it did look like a tree? Well, I could pick any vertex to be the root, just to redraw it. Let's say I picked vertex 1. And then I can just redraw it like this. Now note that this graph and this graph, although they look different, they're exactly the same graph. I mentioned in a previous lecture that a graph is defined by the vertices and edges that it has, right? Now this graph and this graph, they have the same vertices and the same edges. So although they look different, they're the same graph. It doesn't matter what it looks like, okay? It's what's on the inside that counts. Now, once I've picked that root, say, right? Now I know that a tree is acyclic. So that means there can be only one path from any vertex to any other vertex. Okay, so let's take an example 5 and 3. There's this path 5, 1, 3. If there was another path somewhere, let's say 5, 4, 3, that would mean there would be a cycle because there'd be two paths that could join up and make this cycle, right? So knowing that this is a tree means that there's exactly one path between any two vertices. More generally, or more specifically rather, there's exactly one path from any vertex to the root. Okay, so there's a path from 0 to 1. There can only be exactly one path from 0 to 1. If there were two, we'd have a cycle. Okay, now the cool thing about this is it means that we can actually use this to get a more compact representation for trees. So when we represented graphs, we used either an adjacency matrix or an adjacency list, right? And these were potentially large representations. For a tree, we can use something called a parent array. Now in a parent array, we just have one entry in an array for each vertex, right? So here we've got the vertices 0 to 5, so we've got the entries 0 to 5. There's 6 elements in the array. And for every element, the item we store is what the parent of that vertex is in the tree. So if we look at vertex 0, its parent is 3, so we put 3. Vertex 1 is the root, so we make it its own parent just as a way of signifying which one is the root, right? The one which has itself as the parent is the root. Look at vertex 2, its parent is 3. Vertex 3's parent is 1. Vertex 4's parent is 3. Vertex 5's parent is 1. Now, just by keeping this parent array, we've got a complete specification of the graph. If, for instance, I didn't give you this graph and I just gave you this parent array, you'd be able to draw this graph, right? All the edges that are in here and all the vertices that are in here are implied by this parent array. Okay, if you're not clear on that, give it a try. Like, pretend you've never seen this before, and taking this parent array, try and draw a graph to see what it comes out as. Okay, so now we've got a representation for trees. Now I'm going to take you through theorem 5.1, which is the main theorem about trees that's in your book. So if you're following along, you'll see it there as theorem 5.1. And this theorem is quite an interesting one. It says, let T be a graph with n vertices. So that's just the definition. We're talking about a graph with n vertices. Then the following statements are equivalent. T is a tree. T is connected and has n-1 edges. T contains no cycles and has n-1 edges. T is connected and every edge is a bridge. Any two vertices of T are connected by exactly one path. T contains no circuits, but the addition of any new edge creates exactly one circuit. So there's 6 statements here. What do I mean when I say they're equivalent? What I mean is that if any one of them is true, all the rest of them are true. So you could think of it as saying that 4 implies 1, 2, 3, 5, and 6. Or equivalently, 2 implies 1, 3, 4, 5, and 6. Or 1 implies 2, 3, 4, 5, and 6. Or 5 implies 1, 2, 3, 4, and 6. And it's pretty tiring even to just say all of those permutations. So I'm not gonna. But if it's tiring to just say them, can you imagine trying to prove all of those permutations? If I had to prove that 1 implies 2, 1 implies 3, 1 implies 4, 1 implies 5, 1 implies 6, 2 implies 1, 2 implies 3, 2 implies 4, 2 implies... No, not doing it. That's insane. Instead, what I could do is I could make use of some sort of transitivity. I could say 1 implies 2, 2 implies 3, 3 implies 4, 4 implies 5, 5 implies 6, and 6 implies 1. And that would mean they all imply each other, and I don't have to bother trying to prove all of those combinations because that's a nightmare. Okay, so let's look at how we'd prove some part of them. I could ask you to prove any one of them. In a test, I could say, given that T is a graph and T is connected and every edge is a bridge, prove that T is a tree. Okay, then you'd have to go and do that. What I'm gonna do in the lecture is I'm gonna prove the first implies. So I'm gonna prove that 1 implies 2. So T is a tree implies that T is connected and has n-1 edges, assuming T is a graph with n vertices. Okay, so how would we prove that? It's quite a nice result because we know that every tree with n vertices then has n-1 edges, which is kind of cool. Okay, so we're trying to prove that 1 implies 2. T is a graph with n vertices. So we're trying to prove that T is a tree implies that T is connected and has n-1 edges. This is hard to do directly, but we can use induction, same as we did in the previous lecture. Now with induction, we always need our base case. Basically, we need to, if we use the analogy of the previous lecture, we need to make sure that our meme gets out to somebody, okay? We need to make sure that the truth property, if I can put it that way, applies to some item on the number line, Okay, so in this case, we're going to take a base case of n equals 1. So that means T is a tree with one vertex, right? Because it's got n vertices. T is a tree with one vertex, and what we're trying to prove is that it'll have n minus 1 edges, meaning 0 edges. Okay? Now, we need to actually, in real terms, we need to prove that this is true of all graphs of size n. But with n being 1, there aren't many graphs of size 1, right? Any graph of size 1 kind of looks like this, or almost like this. So if we look at it, if a tree has one vertex, there's only one possible edge, is the edge that goes from the vertex to itself, right? Now, can we have that edge in this case? Well, no, because we said that T is a tree, right? We said T is a tree and we're trying to prove that it's connected as n minus 1 edges, but we know it's a tree. Now, if it's a tree, it's connected and acyclic. If it's acyclic, it can't have the cycle that goes from 0 back to 0, okay? So that means it has no edges, which is great, because if it has one vertex and 0 edges, that means it has n minus 1 edges, which is the thing we were trying to prove, right? Is it connected? Well, yes, if I'm at 0, I can get to 0 because I'm already there. So I can get from every vertex to every other vertex because there's only one vertex. And that's the nice thing about base cases, right? They're like kind of stupid. They're really easy to prove. I didn't have to do any work to show that this graph is connected because there's only one vertex, so it's connected because I can get. And I didn't have to prove that it has n minus 1 edges. I didn't have to do any work to prove that. I could just say, well, there's one vertex and there's 0 edges, so that's n minus 1, right? So the base case is quite straightforward. The next thing we look at is the induction step, okay? And how the induction step works, same as it did in the previous proof, is we assume our statement is true for k, and then we want to use that to prove that it's true for k plus 1. Okay. Now in this case, that means we can assume that all trees with k vertices have k minus 1 edges, and we need to prove that all trees with k plus 1 vertices have k edges, right? Because that'll allow us to move the truth along by 1, right? So we know that our statement is true for graphs with one vertex. So if we could prove this, we could move it along to 2 vertices and then 3 and 4 and 5 all the way up to infinity, right? So we'll use a similar strategy to what we did for the graph coloring proof. We start off with saying let T be a tree with k plus 1 vertices. Now, what we want to prove is that it has k edges, right? That's our the thing we want to prove. We need to prove that all trees with k plus 1 vertices have k edges. So we're saying let T be a tree with k plus 1 vertices, and then we want to prove that it has k edges. The problem with this is we know nothing about trees with k plus 1 vertices. Nothing at all. So, I mean, anytime we try to prove something, we want to go like statement 1 implies statement 2, and statement 2 implies statement 3, and we just want to use logic to just keep moving along this set of steps, right? But when we say that T is a tree with k plus 1 vertices, we have nowhere to go because we know nothing about things with k plus 1 vertices. But we do know stuff about trees with k vertices, okay? Because that was the stuff we were allowed to assume in the induction step. We could assume that trees with k vertices have k minus 1 edges. So we want to take this tree that has k plus 1 vertices and turn it into a tree with k vertices because we know things about trees with k vertices. Now, how do we turn something that has k plus 1 vertices into something that has k vertices? I feel like I paused for too long there. We take out a vertex, right? Because it'll go from k plus 1 vertices to k vertices. So what we do is we say remove a vertex v from T to produce T prime. So now we know that T prime has k vertices because it has one less vertices than T. And that's great, but we only know things about trees with k vertices. Is T prime a tree? That's not clear. We know that it's a graph, but we're not entirely sure it's a tree. For it to be a tree, it has to be connected and acyclic. First question I'm going to ask is it acyclic? Is T prime acyclic? Well, T is acyclic, right? Because T is a tree. Now, all we've done to T is we've taken a vertex and its edges out, and we've ended up with T prime. Now, if we start off with something acyclic, and all we do is remove stuff, we can't introduce a cycle, right? There's no way to create a cycle by removing stuff. Okay, so T prime is necessarily acyclic. So that's cool. But is it necessarily connected? And the answer there is no. So here's an example. Let's say I looked at this tree we had earlier. If I remove a vertex v from T, I didn't specify which vertex, so any vertex. Let's say I remove vertex 3. Can I get from vertex 4 to vertex 5? So initially I could have gone 4, 3, 1, 5. But if I take out 3, there's no way to get from 4 to 5, right? So that means I've actually disconnected the tree, right? So T prime is not a tree anymore because it has to be connected. It's not connected if I removed 3, okay? And I didn't specify which vertex to remove, so it could well have been 3. So I can't assume that T prime is a tree, which sucks. So I'm going to change strategies a little bit. I'm going to say, look, removing 3 was a problem. If I removed 3, the tree was disconnected. If instead I had removed 0, then the tree wouldn't have been disconnected, right? If I'd removed 4, the tree wouldn't have been disconnected. I could have gone from 2 to 5 or 0 to 5 without 4 being in the way, right? The important thing is that I'd have to remove a vertex that isn't on the path between any other two vertices, okay? Fundamentally, that means I had to remove a leaf node, one of these bottom ones, okay? The interesting thing about leaf nodes is, if you think of the topology of the tree, they've got a parent, but they don't have any children because they're leaf nodes, right? So they have only one edge. They have exactly one edge is the edge to their parent because they don't have any children. So when I remove this vertex, a leaf node, I'm automatically removing exactly one edge, okay? So I'm changing my rule. Instead of saying remove a vertex v from T to produce T prime, I'm saying remove a leaf node from T to produce T prime, okay? Now, if I remove a leaf node, is T prime necessarily acyclic? Well, yes, because remember T was acyclic and I removed stuff so I couldn't have introduced a cycle. Is T prime connected? Well, now because I removed a leaf node, which didn't have any children, it still is connected, right? Like I said, if I remove 0, I can still get from anywhere to anywhere else, okay? So if T prime is acyclic and connected, then it's a tree, okay? Now T was a tree with k plus 1 vertices, so that means T prime is a tree with k vertices. So that means it has k minus 1 edges. I know that because that's the thing I was allowed to assume, okay? I can assume all trees with k vertices have k minus 1 edges, okay? So that means T prime has k minus 1 edges. Now remember, when I removed V, I said it had exactly one edge that I removed with it. So that means T has just one more edge than T prime. And T prime has k minus 1 edges. So that means T has k edges, right? Just one more. And the only thing I sort of assumed about T was that it was a tree with k plus 1 vertices. So that means it's true of every tree because I haven't made this specific. So every tree with k plus 1 vertices has k edges, okay? So that means our induction meme has gone viral. I've successfully used the induction step to say that if the truth applies to item k, then it applies to item k plus 1. Okay? So that means 1 implies 2 for all trees of size k for all natural numbers k. Or a simpler way to say it is that 1 implies 2 for all trees. So I hope you're getting the hang of this induction thing a little bit. Basically, when it comes to graphs, I kind of say, look, base case, I got to pick something. I'm going to generally pick n equals 1 or even n equals 0, but 1 is often a bit easier to look at. So in this case, I chose n equals 1, and that was my base case. And then I want to prove that if it's true for k, it's true for k plus 1. And how I do that is by starting off with a graph with k plus 1 vertices and removing a vertex. In this case, I removed a leaf node to get to k. In the previous one on graph coloring, I removed the vertex with maximum degree, right? So you gotta think about it a little in what properties you need that vertex that you remove to have. But basically the steps were quite similar for the graph coloring one and for this trees having n minus 1 edges proof. So it's quite induction is quite a useful thing to do on these graphs. Okay, so the next thing is I want you to read section 5.1 and section 5.3 in the book. 5.3 is about depth first search and breadth first search. Now, they're slightly different to the algorithms you did last year in Richard's course. They're more about constructing and keeping a depth-first search and breadth-first search tree. Okay, so it's not just necessarily about getting from some vertex to any other vertex. It's about constructing a tree that represents either a depth-first search or a breadth-first search. Okay, so they're all about sort of creating parent arrays. The breadth-first search in particular is super useful for your assignment. It's a pretty good algorithm to use. A star is probably better, but also a lot more difficult. So consider using breadth-first search. It's a winner. You'll definitely beat the medium agent if you use breadth-first search, and you'll probably beat most of your classmates as well. So the intention is not to give a lecture on depth-first search or breadth-first search. You've already done a lab on depth-first search. And I think Richard has covered these topics pretty well, depth-first search and breadth-first search. So I'm not gonna go through it pretty heavily. This week there will be a quiz that will include stuff on trees, depth-first search trees, breadth-first search trees. Okay. In the next lecture we'll talk about minimum weighted spanning trees. But before that, I will be following the WhatsApp group just to see if you guys do need a lecture on depth-first search and or breadth-first search trees. I'm happy to give them. The intention is not to do that because I think it's stuff that is covered pretty well in the book. But if there is any request for it or sufficient request for it, I'm happy to do it. So yeah, it's quite a short lecture this week. Thanks for listening.